So when you're thinking about scalability in a blockchain app, it's all about how the network handles growth. You know, nodes joining, transactions increasing, that sort of thing.
Yeah, especially with public blockchains where anyone can join.
Exactly. And one big issue is transaction throughput. If you're designing for high-frequency trades or something similar, you need to think beyond just basic consensus algorithms like proof of work. They can become bottlenecks really quickly.
I've been looking into sharding as a solution for that.
Sharding's definitely an interesting approach. It essentially breaks up the ledger into smaller chunks so each node doesn't have to process everything. But there's complexity in maintaining consistency across shards and making sure no shard becomes a bottleneck itself.
That does sound tricky.
Tricky and risky. Another consideration is state management. How do you keep track of all those states without blowing up your storage needs? There are techniques like pruning old data, but then you lose some historical context which could be critical for certain applications.
Pruning sounds like it might introduce its own set of issues though.
Absolutely. It's a trade-off between performance and completeness. And don't even get me started on cross-shard communication. The synchronization overhead could kill your efficiency gains if not handled properly.
So what would you suggest as the best starting point?
Start by defining clear goals and constraints based on expected usage patterns. Then look at hybrid models, maybe combining different types of consensus mechanisms, or even integrating off-chain solutions like payment channels. But remember, every tweak increases complexity and potentially introduces new vulnerabilities.
Gotcha. So it's really about balancing out the trade-offs.
Precisely. And always test extensively under simulated load conditions. Real-world scenarios often expose flaws that aren't obvious during development. Like that time we thought our algorithm was solid until someone decided to run 1,000 transactions per second. Speaking of which, let's talk about consensus mechanisms. They're crucial for ensuring that all nodes agree on the state of the ledger, but they also have a significant impact on performance.
Definitely. Different mechanisms seem to favor either speed or security.
Right. For instance, proof of work, POW, is known for its robustness, but is notoriously slow and resource-intensive. On the other hand, proof of stake, POW, aims to address those issues by being more energy efficient and faster.
POW seems to be gaining traction due to these advantages.
True, but POW comes with its own set of challenges. It can suffer from issues like centralization, because validators are chosen based on how much stake they hold. This might not align well with the decentralized ethos many blockchain projects aim for.
That decentralization aspect is important.
Absolutely. Another mechanism worth considering is delegated proof of stake, DPoS. It's designed to improve scalability and governance by having a fixed number of delegates elected by stakeholders to validate transactions.
DPoS sounds like it could streamline things quite a bit.
Yes, it can lead to faster block times and better performance. However, it reduces decentralization since only a few entities control the validation process. So again, you're trading off decentralization for efficiency.
It's really about finding that sweet spot then.
Exactly. And don't forget about Byzantine fault tolerance, BFT, systems like Practical BFT, PBFT. These are great for private or consortium chains where trust among participants is higher and you need fast finality.
PBFT seems ideal for certain use cases then.
Sure thing. Just keep in mind that, while PBFT offers fast transaction confirmation, it requires a trusted setup and doesn't scale well beyond a certain number of nodes due to its quadratic message complexity.
So there's no one-size-fits-all solution here.
Never is. Each consensus mechanism has its strengths and weaknesses depending on your specific requirements. You've got to weigh the trade-offs carefully and choose what works best for your particular scenario. Yeah, and another big challenge with public blockchains is privacy. Everyone can see every transaction on the ledger, which can be a deal breaker for many applications.
Absolutely. How do you typically address that?
Well, one approach is using pseudonymous addresses instead of real identities. But that only goes so far. To really protect privacy, you need more sophisticated solutions like zero-knowledge proofs or ring signatures.
Zero-knowledge proofs sound intriguing.
They are. Essentially, they allow you to prove something is true without revealing any information beyond the truth of the statement itself. Perfect for maintaining confidentiality while still verifying transactions.
That sounds like a powerful tool.
Indeed. Another method is homomorphic encryption, where computations can be performed on encrypted data without decrypting it first. This way, sensitive data remains protected throughout the process.
Homomorphic encryption seems complex but useful.
It certainly adds a layer of complexity, but it's worth it if privacy is a top priority. And let's not forget about mixing services or tumblers, which help obscure the origins of funds by mixing them together before redistributing.
Mixing services add another level of obfuscation then.
Exactly. All these techniques aim to strike a balance between transparency, which is fundamental to blockchain integrity, and user privacy. You've got to pick the right tools based on your specific needs and constraints.
So it's really about layering multiple approaches for comprehensive protection.
Precisely. No single technique will cover all bases, so combining several methods gives you a robust framework for handling privacy concerns effectively. Speaking of which, let's touch on smart contract security. It's a critical aspect given how much value is tied up in these contracts.
Absolutely. What are some common vulnerabilities you've seen?
Oh, there are plenty. One big one is reentrancy attacks, where a malicious contract calls back into the original contract before it finishes executing, potentially draining funds.
That sounds dangerous.
Very much so. Another classic issue is integer overflow and underflow. If you're not careful with arithmetic operations, it can lead to unexpected results that attackers can exploit.
Integer overflows can be tricky to catch.
They definitely can. And then there's the problem of external call vulnerabilities. When a contract interacts with untrusted code, it opens itself up to all sorts of risks.
External calls seem like a double-edged sword then.
Exactly. You need them for functionality, but they require rigorous testing and validation to ensure nothing goes wrong. Formal verification methods can help here by mathematically proving that the contract behaves as intended under all conditions.
Formal verification sounds thorough.
It is, but it's also time-consuming and requires specialized skills. Automated auditing tools can also be very helpful in catching common mistakes early on in the development process.
Automated tools can save a lot of headaches.
For sure. But, ultimately, good coding practices and thorough peer reviews are still essential. Making sure your team understands the potential pitfalls and adheres to best practices can go a long way toward preventing issues down the line.